Hello guys, how are you today? So today I'll be explaining the physics course practice section 6.6 to 6.10. So let's start with the first question. In the first question they said, a pulse in a rope reaches its end, which is free to move up and down a pole. Which of the following will happen to the pulse upon reflection? So by looking over here, you can see that it is what? That it is a free-ended reflection. Okay, what's gonna happen is that it's gonna be a free-ended reflection. However, if it was like this, let us say, then this is what? This is a fixed-ended reflection. Okay, so some characteristics you need to know about the free-ended reflection is that the pulse remains upright. So pulse is, we'll not say upright, the pulse is not inverted. Okay. Then we have that the speed of, so we also have that the speed, the frequency, the wavelength, and the amplitude all remain the same. Okay, so in the free-ended reflection, we have that the pulse is not inverted. However, the speed, frequency, wavelength, and amplitude remain the same, and the direction is changed. This is for what? This is for the free-ended reflection. However, for the what is it called? The fixed-ended reflection, we have that the pulse is inverted. But then we also have what? We have that the speed, frequency, wavelength, and amplitude, they also remain the same. And however, the direction is also changed. Alright, so which of the following will happen to the pulse upon reflection? Because it is a free-ended wave reflection, what's going to happen is that the pulse is not inverted, the frequency will remain the same, the speed will remain the same, the wavelength will remain the same, and the amplitude will also remain the same. We move on to question number 2. A rope is made of two pieces, one denser than the other. So let's say this is the thin rope and this is the denser rope, okay? An upright pulse is emitted from the lighter piece towards the denser piece. So what's going to happen is that you're going to have a pulse that will go from the lighter piece to the thicker piece. What we need to know about the behavior is that if we are going from lighter to thicker, okay, if we are going from lighter to thicker, we are going to have an inverted reflection. Okay, we're also gonna have a slower speed, so slower speed in the thicker. We are also gonna have that the wave is gonna be upright in the thicker. And we will also have that the wavelength decreases. So from lighter to thicker, we're gonna have inverted reflection, slower speed in the thicker wire, upright in the thicker wire, and the wavelength is gonna decrease. However, if we are dealing from thicker to lighter, so thicker to lighter, let us say thicker to lighter, it is like this. This is thicker to lighter, so if you're gonna have the wave, it will look like this. My bad, there you go. Okay, so if the wave is gonna go from the thicker to the lighter, then we will have that it is reflected, okay, upright. So the reflection is gonna remain upright. The wavelength is gonna increase, so wavelength increases. The frequency is gonna stay the same, so frequency stays the same. The frequency also stays the same over here, okay? So from lighter to thicker and thicker to lighter, the frequency is always the same. And then it is faster in the thinner wire, and it is also gonna be upright in the thinner wire. So from thicker to lighter versus lighter to thicker. Here we're moving from the lighter to the thicker. So what's going to happen is that there's going to be an inverted reflection. We're going to have a lowered speed, so there will be a lower speed, and the wave is transmitted. That means the wave will go from the thinner to the thicker in an upright manner. Okay, let's move on to question number 3. In question number 3, they said in order to locate their prey, a bat sends out sound waves. When the sound waves hit an object, they bounce off the object and return to the bat's ears. A bat listens to the echo produced and figures out where the insect is and how big it is. A bat can emit sound from 12 kHz to 160 kHz. Given that the speed of sound in air is 340 meters per second, fill in the blanks. The sound with the longest wavelength that a bat can produce to the nearest integer. Okay, to do this, to find the sound with the longest wavelength, we're going to take the speed of sound, which is 340 meters per second, and we are going to divide it by the smallest frequency. So the smallest frequency in this case, it is, okay, so you are going to get the answer to be 28.333. So they need it to the nearest integer, you will put it 28 millimeters. So again, okay, the sound with the longest wavelength that a bat can produce to the nearest integer, it is what? It is. So the equation, my bad, it is, they want the wavelength, which is lambda. Lambda, it is equal to the speed over the frequency. So you're going to take the smallest frequency because they want the longest wavelength. The smallest frequency, which is 12 kilohertz, you're going to keep it in kilohertz and you're going to keep it in meter per second. You will get your answer in millimeter, okay? So 340 meters per second divided by 12 kilohertz, you're going to get 28.333. You will round it approximately 28 millimeters. Now, the bat hears the echo 0.050 seconds after it screeches. The insect that sound waves bounce off to 1 decimal place is how many meters away? So first thing we need to know is we're going to take the speed of sound in air, which is 340 meters per second. We're going to multiply how many seconds it took for the wave to bounce off, so 0.05 seconds, and we're going to divide it by 2, because look what happened. He sent it and it returned back in how many seconds? In 0.050 seconds. So we need to find only the distance, which is, let's say, from him sending the wave. So you're going to divide it by 2. So it's going to be 340 times 0.05 divided by 2. You will get the answer, which is 8.5 meters. We move on to question number 4. In question number 4, they said, a stone is thrown into a lake. After 2.6 seconds of this event, a photo of the lake surface is taken and shown in the diagram below. The dark fringes represent the peaks of the water wave. The smallest graduation of the grid represents 20 centimeters. Okay? So, the water wave can be classified as, because it needs a medium to propagate. If it needs a medium to propagate in, then it is what? It is mechanical. Okay? The water wave can be classified as what? Because displacement of the particles is perpendicular to the wave propagation direction. If it is perpendicular to the wave propagation direction, then it is transverse. Okay? Fill in the blanks. The wavelength of the wave to 1 decimal place. How do we find the wavelength of the wave? We know that each graduation of the grid is 20 centimeters. And one wave, let us say, we can take it from here until here. Okay, this is the wavelength of one wave. It is gonna be what? It is gonna be 1, 2, 3, 4 blocks. So 4 times 20 centimeter, which is 80 centimeter. Now, if you go down, they want it in meters. So 80 centimeter, to change it to meter, you will need to divide by 100. So you will get 0.8 meters. Now, the speed of the wave to 1 decimal place. To find the speed of the wave, we know what? We know speed. It is equal to the distance traveled over the time. So let us find the total distance traveled, because they said after 2.6 seconds, this is the total image. So the total distance traveled from this center over here until this point all the way over here, it is how many blocks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 blocks. So 16 times 20, that is 320 centimeters. If you change it to meters, this is 3.2 meters. So now you have the distance. You're going to divide it by the time, which is 2.6 seconds. So 3.2 divided by 2.6 seconds, you will get your answer to be approximately 1.23. So it is 1.23 meters per second. Now they need the frequency. We know that the frequency is equal to what? It is equal to the speed over the wavelength lambda. So frequency is equal to the speed, which is 1.23 meter per second, over the wavelength, which is 0.8 meter. So 1.23 over 0.8, you will get an answer which is approximately 1.54 hertz. So this is what the frequency. We'll move on to question number 5. In question number 5, they said, the diagram below represents crests of the wave forming through the medium. The smallest graduation of the grid represents 10 centimeters. The wave propagates from S to A in 4 seconds. They told us, the crest at A becomes a trough. So look, we know that from S to A, it took how many seconds? It took 4 seconds. So from crest to crest, it took 4 seconds. So let us project it like this. Okay? From this crest here till this crest here, it took how many seconds? 4 seconds. But they need what? They need from this crest here till this trough here. It will take half of the time, which is 2 seconds. Very simply. As the crest at A becomes a trough and then a crest again, the wave propagates by another. So they said again, my bad. They said again, this is what we are dealing with. Okay, they said as, please go down. Okay, thank you. As the crest, my bad. As the crest becomes a trough, so this is the crest, it became the trough, and then it became a crest again, which is this distance over here. They need how many centimeters this wave will propagate. So we know from S to A, it is what? It is from crest to crest. So let us move, let's say theoretically A is going to be over here. So it's going to be 1, 2, 3, 4, 5, and 6 blocks, okay? And how many centimeters is each blocks? It is 10 centimeters. So the total distance for it to become crest to crest, it is going to be 60 centimeters, okay? So now we move on to question number 6. In question number 6, they said, consider a light passing through a small slit projected on a screen. The light pattern obtained on the screen is shown below. What is the phenomenon being observed? As you can see over here, we have light passing through a small slit. Whenever you see light passing through a small slit, you will know that this is diffraction. Now they said, when the phenomenon what phenomenon explains the fact that several additional light fringes are seen on the left and right of the central slit? So look what's happening. We have that the waves, they are coming from here and from here, and they are joining together to form one big wave at this specific position over here. So let's say it's like this. Okay, it's going like this, this is going like this. When they meet, they will form one big wave. And this one big wave is this one over here. So what do we call this? We call this phenomenon constructive interference. Okay, so basically they are adding up together to form this big light pattern. We move on to question number 7. In question number 7, they said Arago spot is a bright point that appears at the center of a circular object's shadow. This bright spot is surrounded by several light circles. The ray diagram that explains the formation of the Arago spot is shown in the left diagram below. The magnified image of the Arago spot is shown in the right diagram. They said, which of the following explains why rays of light change their direction of propagation on the edge of the disk? So when they change their direction of propagation, this is known as diffraction, okay? Now, which of the following best explains the formation of the bright spot? So again, when there is a bright spot, okay, and everywhere else is dark, this is what? You have a wave over here, going like this, They will join together to make one big bright spot, and we call this constructive interference. So now we move on to question number 8. They said, when a friend is talking to you from behind the corner, you can still hear him even though you can't see him. Which phenomenon allows you to hear this person? Well, it is because of the diffraction of the sound waves. So the sound waves will diffract, okay? And this will cause what? This will cause you to be able to hear him even though you cannot see him. We move on to question number 9. They said two pulses of equal amplitude in the opposite sense are moving towards each other and meet at a point A. Which of the following phenomena occur at A? This is destructive interference because they're in the opposite sense moving towards each other. Okay? We move to question number 10. They said two pulses of amplitude 5 centimeter and 3 centimeter, they told us, meet at point O. They told us if the pulses interfere constructively, that means they will add. So 5 plus 3, it will give us 8 centimeters. Destructively, they will subtract. 5 minus 3, it will give us how many centimeters? 2 centimeters. So 8 and then 2 centimeters. We'll move to question number 11. They told us a plane wave strikes a straight reflector as shown below. Select the diagram that shows the correct path of the reflected wave. You will see that it will go like this, and you will draw first of all the normal. The normal will look something like this. Okay, and based by the reflected rule, you will have that the angle will be something like this. And do not forget also about the waves. So it will have to look something like this. Which one is it? It's definitely this one over here. We'll move on to question number 12. They told us a ripple tank is said to hold 2 regions of water, deep and shallow water. An oscillator is used at one end of the ripple tank to create a water wave as shown below. Drag and drop the correct terms to compare the properties of the water wave in the deep water to the properties of the water wave in the shallow water. So because we are dealing with what? We're dealing with the waves in deep water and shallow water. So here you have to pay attention and remember something very important. The frequency always stays the same in both the deep water and the shallow water. However, the wavelength is gonna be greater in the deeper water than in the shallow water. And because the wavelength is greater in the deeper water than in the shallow water, that means what? That means the wave speed is gonna be greater in the deeper water than in the shallower water. So remember, when we are dealing with the properties of a refraction, the frequency and the period will stay the same. However, the wavelength and the wave speed and literally anything else, for example, I don't know, whatever, yeah, they will change depending on whether you are going from the deeper to the shallower. So going from deeper to shallower, the wavelength will decrease and the wave speed will decrease. Okay? We move on to question number 13. They said 2 pulses whose shapes are shown in the diagram move towards each other and meet at point A. So what's gonna happen is constructive interference. They will add on top of each other. And the shape of pulse P after it passes A, it's gonna be exactly the same as it was. So you will choose this one over here. Now this phenomenon, we know that this is constructive interference. We'll move on to question number 14. In question number 14, they said 2 pulses are shown in the diagram below, moving towards each other and they meet at point A. So this is destructive interference, so they're gonna have leave a gap in each other in some sense. Now the shape of Q after it passes A, it's gonna be the same exactly as it was before. So it's gonna look like this. Now this phenomenon, as we said, that is destructive interference. Now we move on to question number 15. In question number 15, they told us a sound wave train is sent towards a concrete wall at time 0 second. It reaches the wall at 0.2 seconds and reflects off of it. If it will reflect off of the wall, that means the diagram is also gonna be reflected in this manner. So take as 0.2 is the wall, it will come like this, and then it will be reflected on the other side. Okay, so you're gonna choose this graph over here. Assume that the sound wave partly refracts into the wall, okay? So let's say it will refract into the wall. What properties will remain the same upon refraction? The only 2 properties that remain the same upon refraction, they are frequency and the period. Okay, we move on to question number 16. In question number 16, it says seismic waves are mechanical waves that propagate through Earth's interior after earthquakes or volcanic eruptions. The diagram below shows the direction in which a seismic wave passes through the Earth's crust. The frequency of the wave is 8 Hz. The pulse travels from A to B in 0.1 seconds. Now, what's happening here, as you can see, it is what? It is refraction, because you can see that the wavelength is changing. If the wavelength is changing, then this is definitely refraction. Okay, so they want us to find in part A the speed of the wave as it travels from A to B. Very simply, to find that, first of all, I'm going to find the wavelength from A to B. To find the wavelength from A to B, I'm going to apply Pythagorean theorem. So this over here is 400 meters. This over here is 300 meters. Take them from the graph, okay? And to find the value of AB, I will apply Pythagorean rule. So radical 400 squared plus 300 squared, you would get that this is 500 meters. Okay, so now we know that it is 500 meters. But they want it in which value? They want it in kilometers. So 500 meters, change it to kilometer, it will be 0.5 kilometers. Now, they want the speed. So we are given what? We are given the wavelength and we are given the time. or not the wavelength, let's say the distance. We are given the distance and we have the time. So to find the speed, we are going to do the distance, which is 0.5 kilometers, over the time, which is 0.1 seconds. So you will put them on top of each other and you will get 5 kilometers per second. That's a very big distance, okay? Now the wavelength of the wave as it travels from A to B, now we can find the wavelength. So we have the frequency over here, it is what? It is 8 hertz, okay? And we know that the equation to find the wavelength, it is that wavelength is equal to speed over the frequency. So the wavelength lambda, it is equal to the speed, which is 5 kilometers per second, or 5,000 meters, which is preferable, per second, divided by what? Divided by the frequency, which is 8 hertz. You will put it together and you will get that the wavelength, it is 625 meters. So this is 625 meters. Now the frequency of the wave as it travels from B to C is 8 hertz, because look, we said that this is a refraction, because as you can see the wavelength is changing, or the speed of the wave is also changing. So because this is refraction, the only thing that will not change upon refraction, it is the period and the frequency. Now the wave changes its direction of propagation at points B and C due to what? Due to refraction. Okay, very simply, this is all we need to know from question number 16. We move on to question number 17. Here, which type of radiation whose wavelength is longer than that of visible light but shorter than microwave radiation? So here you should memorize these. You have infrared radiation, okay? Or sorry, no, forget about that, my bad. I just gave you the answer, sorry. Okay, so you have radio waves, then you have microwaves, then you have infrared, and then you have visible light, and then you have X-rays, and then you have gamma rays. I think I may have forgotten over here to put that it is ultraviolet light, which is after the visible. So again, if I want to do it again, it would be radio waves, microwave, infrared, visible light, X-rays, I forgot again, UV light, X-rays, and then gamma rays, okay? So please remember this order. They said, what is the type of radiation whose wavelength is longer than that of visible light, but shorter than that of microwave radiation? What you need to know is that wavelength increases like this. So they want something that is longer than visible light, so everything here is longer than visible light, and shorter than microwave radiation. So you're left with this one, which is the infrared radiation. We move here. They said the type of radiation identified in part A passes from air to water, so it will experience refraction. If it experiences refraction, then the frequency and the period will remain the same. However, because it is an infrared radiation, which is a type of light or a type of electromagnetic radiation, then the speed and the wavelength are gonna decrease if it's going from a less dense to a more dense. So the speed will decrease and the wavelength will decrease. However, if we were thinking of a mechanical wave, then it would be the opposite. If it was going from air into water, then definitely the speed would increase and the wavelength would increase. Okay, we move on to question number 18. In question number 18, it says, what part of the electromagnetic spectrum does this electromagnetic wave belong to if it has 120 nanometer in vacuum as a wavelength? So here, all you need to do is check the electromagnetic waves, okay? So over here, they don't have the, here we go, this one. As you can see, ultraviolet radiation, it is what? It is 10 to the power of minus 8 and 10 to the power of minus 10. So the value of ultraviolet radiation, it is in between 10 to the power of minus 8 and 10 to the power of minus 10. Let us go back. We have 120 nanometers, which is 120 times 10 to the power of minus 9, which is, in another sense, 12 times 10 to the power of minus 10. So as you can see, or no, it's not minus 10, my bad. 12 times 10 to the power of minus 8. My bad, I did a very wrong miscalculation. So it goes from 120 times 10 to the power of minus 9. You will change it, it will become 12 times 10 to the power of minus 8. As you can see, it is in the range of the electromagnetic spectrum of ultraviolet, so definitely it will belong to the ultraviolet radiation. Now they said, the frequency of this electromagnetic wave is how many hertz? What is the frequency of this electromagnetic wave? It is very simply this formula. We know that frequency is equal to the speed over the wavelength. So we're going to take the speed of light, which is 3 times 10 to the power of minus 8. This is the speed. We're going to divide it by the wavelength, which was 1.2 times 10 to the power of minus 7. Or we can take it as it was before, which is 120 times 10 to the power of minus 9. You will put it on the calculator, okay? And you will get an answer, which is what? Which is 2.5 times 10 to the power of 15. So very simply over here, it is 2.5 times 10 to the power of 15 hertz. We move on to question number 19. Here again, you have to remember the electromagnetic waves. So we have radio has the biggest wavelength, then micro, then infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. Okay, so they said drag and drop the correct answer based on what? Based on the wavelength. So here it's radio waves, then it's supposed to be microwaves, then after microwaves it's infrared, then after infrared it is visible light, then after visible light it is the ultraviolet light, and then after the ultraviolet light it is the X-rays and the gamma rays. Now choose the correct answer to complete the sentence below. The type of electromagnetic radiation are arranged in order of increasing wavelength. Because as you can see, it is going towards the right. So the more you go to the right, you will see it's going towards the radio waves. And you can see that definitely the radio waves have the greatest wavelength. Now the diagram below shows a ripple tank as seen from above. An oscillator is generating a straight water waves towards the gap. So how will the water waves behave as they pass through the gap? As they pass through the gap, they are gonna diffract. So diffraction is gonna occur, so they will be diffracted. Now we move on to the last question, which is question number 21. They said the diagram below shows some water waves passing through a gap between two stepping stones. Okay? Which factors affect the amount of diffraction of these waves? So first of all, let us say you have this stone over here and this stone over here, and then you have the water waves. They will diffract like this. Okay, they will look like this. This is how their diffraction will look like. But if you separated them even further and you continued, the diffraction would look then something like this. Okay, now another thing would be the size of the wave or the wavelength. So let's say you had two stones separated like this. If it was like this big, then definitely it's gonna diffract. Okay, however, if it was small and it passes through the gap, it's not gonna diffract. So the amount of diffraction of these waves, it depends on the width of the gap and the wavelength of the water waves. Let us submit, and hopefully I'm praying we don't have any mistakes. And thank God we don't have any mistakes. Thank you guys for watching. I hope you enjoyed and have a wonderful day. Just waiting for it to load. There we go. Thank you guys. I really hope you enjoyed and have a wonderful day.